and I'll talk to you today about the inhibition and control of ethylene. Let's talk first about the beneficial effects of ethylene. Ethylene promotes faster and uniform ripening, and this is very useful for plants like banana, tomato, avocado, or pear. It also acts as a degreening agent, especially for citrus. It degrades chlorophyll. As we know, chlorophyll is a green pigment in the skin of the fruit, and by degrading it, you get the orange flesh that we all know for oranges. It also helps abscission for plant parts from the plant, and it's good for harvesting, for easy harvesting. A little bit about the detrimental facts of ethylene. That's what we don't want to happen. Ethylene accelerates ripening and softening of the fruit. It also accelerates yellowing of leafy greens, beans, and cucumbers. Broccoli yellowing is a problem, and the opening of florets, as you can see on the top left here. You get bitter compounds in carrots with high ethylene in the storage place, as well as russet spotting, as you can see here on lettuce. Asparagus spears become tougher when there is a high ethylene amounts in the storage place. Leaves from potted plants, like you see on the bottom here, fall, as well as flowers very often. Petals fall, as I said, and you get sprouting of potatoes, onions, etc. Here's an example of Hass avocado, for example, stored at a controlled atmosphere, 2% oxygen and 2.5% CO2. And you have 4 different amounts of ethylene in the storage room, plus air control. And you see how 10 ppm ethylene has a significantly detrimental effect on the condition of the avocado. What are the sources of ethylene? There can be internal and external sources of ethylene in the cold room. Internal sources is the plant itself. Plant parts, even if they're cut from the tree, still produce ethylene. They're still alive. They're not dead when you cut them. So you get ethylene accumulation in the room over time if you don't have good ventilation. External sources could be combustion engines like trucks and forklifts, smoke of any type, ripening rooms that have leaks or are not well sealed, rotting fruit and vegetables on the side of, for example, of a ripening room, as well as fungi, external fungi on fruit. Here's an example of how much ethylene we find in many different situations. Just to give you an idea, 1 ppm is 1,000 parts per billion, as you know. 1 ppm, if we translate it into time, is 1 second in 11 and a half days. 1 part per billion is 1 second in about 32 years. So in rural conditions, you have 1 to 5 ppb, parts per billion of ethylene. In urban, where you have combustion engines, you have less than 50 parts per billion. In heavy traffic, less than 1,000 parts per billion. And then if we go to a distribution center that's well ventilated, you get less than 13 parts per million, much higher. Processor, where you have a lot of plant parts coming in and being chopped or packed, you have about 133 parts per million. Retail, usually you have good air ventilation, air circulation, so you get less than 2 parts per million. And in flower coolers, you get about 13 parts per million. In cold storage, when you have a cold storage of apples and pears, you get less than 30 parts per million, and in controlled atmosphere storage, you get significantly higher amounts of ethylene because ethylene is building up in the CA room. There is no air circulation or ventilation actually of the CA storage. In a household fridge, you get, when you have apples stored in there, you get about 0.2 parts per million, whereas when you have no apples, you get about 0.029 ppm, much less. Let's talk now about how we can overcome the ethylene effects, and we'll start with reducing or inhibiting the ethylene production itself. As you probably know, ethylene production increases by increased maturity, increased ripening, and stress. So if your product has gone through stress, through like rough packing lines, or has been on trucks for a long time, it will produce more ethylene than product that has been sitting in the cold room. You can decrease ethylene by lowering the temperature that you hold your product at, and also by reducing the oxygen levels in the room. On the bottom here, you see flowers that have been stored at 4 different temperatures. The higher the temperature, the more ethylene you had in the room, and the more senescent flowers you had. So you see 20 compared to 0, huge difference. Here's an example from Beth Mitchum, who's worked a lot on, with pears, of the effect of ethylene on Bartlett pears after a 3-month storage. You have 2 different temperatures. The low one on the right, -1 degree Celsius, and on the left you have 2 degrees Celsius. And you see 2 tiny amounts, small amounts of ethylene. 0 actually, non-existent. They used scrubbers to scrub the ethylene out of the room, and 1 ppm. You see how in the lower temperature there was no significant effect of higher ethylene presence. However, on the higher temperature at 2 degrees C, you see how 1 ppm induced scalding on pear significantly. So low temperature suppresses ethylene action. Inhibition of action of ethylene. Controlled or modified atmosphere. As I mentioned before, high CO2 reduces the respiration rate of the plant parts. And this means that you reduce the production of ethylene as well. It also does reduce the sensitivity of the product to ethylene. So you see on the left an older picture here where peppers have been stored for 10 days, for 21 days at 10 degrees. And on the left, it was 21% oxygen and 0% CO2, ambient conditions. And on the right, controlled atmosphere, 2% oxygen, 10% CO2. You see the peppers, they turned red on the left and they stayed green on the right. Examples here, Textrol is a pallet seal system where they use a plastic shroud. They cover pallets usually with berries here in the States. They flush in high CO2 air, and then they seal it on the bottom, and they ship it cross-country. And this is supposed to extend the shelf life by, keeping the ethylene lower in there. Low oxygen delays ripening of Santa Rosa plums. You see Santa Rosa plums stored for 5 weeks at 10 degrees in air, or 1% oxygen plus 5% CO2. You see how more apparent the purple color on the air stored plums is. Let's move to inhibition of action of ethylene. Silver compounds like silver thiosulfate is a way to inhibit the ethylene action. Mainly, it's only used actually for ornamentals. Humans should not consume silver, it's not good for you. You probably know that. So you see here the effect of silver thiosulfate on carnations, the shriveling of the flowers. On the left, you see silver thiosulfate treated carnations and control when they were 10 days in a container with ethylene. Similarly, zygocactus on the left, control versus treated ones, and delphinium on the bottom. Let's continue to inhibition of action. 1-methylcyclopropene, or 1-MCP, is a very powerful regulator of fruit ripening. It's a non-toxic chemical, it's a gas usually, and it can bind irreversibly to the ethylene receptors of the plant part. Imagine the MCP like a bad key that will get in a lock and will just break it, and then the plant will not be able to perceive the ethylene that's in the room. So, however, many plants can produce more receptors later. So if there's no MCP in the room, they will be able to perceive ethylene and ripen normally. However, one of the issues is it's very easy to overdose when treating fruit commodities. And then this will result in poor final quality. MCP is used It's complicated because, as I said, fruit maturity and ripeness at application, as well as the concentration, the exposure time, along with the temperature during and following treatment, play a very important role on how effective it is and how the ripening will continue after the application. It's very important for you to determine where and when MCP can be used and if it can add value to the fruit category. And there's many commercial types like ethyl block sachets, Smart Fresh and Smart Tabs, and here's some commercial packages. Here's how MCP looks. This is ethylene, you see the 2 carbons, and here's MCP. So that's how it binds to the receptor and it tricks the plant. It's attached there, it locks the receptor, and then it stays there. So there's ethylene in the room, but the plant cannot sense it. However, when new receptors form, ethylene can get there, and then it can perceive the presence of ethylene. Examples of 1-MCP effects in plants, they can be transient, as I said. If there's new receptors forming after 3 days, for example, in this case, plants that were exposed to ethylene showed the effect of ethylene with degradation of air quality. The major commercial use of MCP is in apples. That's the biggest target crop for methylcyclopropene. It works very well. It reduces internal ethylene concentrations in the fruit. It can delay effectively softening, and you get crisper apples. That's why apple quality today is much better than compared to 15 or 20 years ago. It also reduces effectively superficial scald, and that's here an example. On the left, you see treated apples with MCP and control apples on the right. Here's a photo of MCP treated avocados. These avocados were stored at 5.5 degrees C for 4 and 7 weeks. And we used, actually Mary Lou, I think, worked on this project, 3 different concentrations of MCP, 0, 10, 0, 100, and 250 parts per million. For shorter durations, you don't see a significant effect of MCP. However, for 7 weeks of storage, you see how the control fruit had a significantly worse quality compared to the treated fruit. Bananas. MCP can delay browning, brown spots, sugar spots in bananas. In this experiment here, they used color stage 3 bananas, and they treated them for 6 days with 4 different concentrations of 1-MCP. 0, 300, 450, and 600 parts per billion. So if you compare the high concentration of MCP compared to the control one, you see a significant effect in the reduction of brown spots. More examples here of the effect of 1-MCP in different crops. You can see pears on the left, control versus 1-MCP treated, dragon fruit, eggplant, and so forth. How we can overcome the ethylene effects? Another way is to avoid ethylene, and that's also very important. You want to keep ethylene sources away from ethylene-sensitive products. As I said earlier, vehicles, floor polishers, forklifts that are not battery operated, decaying products, and exhaust from ripening rooms are issues that can cause high ethylene amounts in your distribution center. You want to avoid, that's very important, mixed loads and mixed shipments of ethylene producers and ethylene responders. And it's very interesting to see that ethylene production doesn't necessarily mean ethylene sensitivity. And here is a table of a few crops. For example, on the left you see crops that produce low amounts of ethylene but are highly sensitive to it. And that's kiwi fruit, mature green tomato, watermelon, and plantain, as well as vegetables like spinach, brassicas, and herbs. And on the right you see products that produce moderate to high ethylene production but are not sensitive to it. And Barbara mentioned that earlier, ripe tomato, feijoa, and figs. I think now that's the industry standard. We use battery-operated forklifts in enclosed areas to avoid ethylene production. And we avoid, that's an old picture, luckily, you avoid storing ethylene-producing and ethylene-sensitive commodities. In this case, they stored apples and lettuce. That's a big, big no-no. Sanitation. It's an old picture, and you cannot see probably here. There's like decaying plant material on the ground and on the sides. These all produce ethylene as they rot. So you don't want to do that. You want to keep your DC clean and remove all the decaying plant material out of it. Ethylene removal. That's a very important part for every operation. Ventilation, changing the air, 1 air exchange per hour, is the cheapest and most efficient way of reducing the ethylene presence in an enclosed room. You want to measure the concentration of ethylene and make sure it remains below the threshold. There is a number of oxidizers that what they do is they oxidize ethylene to CO2 and water. And some of these are ozone, potassium permanganate, photocatalytic oxidations, and UV lights. There are also sorbents that sort the ethylene from the atmosphere, and some of these are activated carbons, clays, zeolites, and palladium-based products. Ethylene oxidation. Here's, like, for example, the use of UV radiation or ozone, and that's how it works. You get ethylene plus ozone, and it's getting broken down to CO2 and water. However, it happens very often that high amounts of ozone can cause injury to fruits and vegetables, so they end up having a negative effect in the quality of the fruit overall. Here, this potassium permanganate examples, and this generator here on the right uses pellets, potassium permanganate pellets, and these are other ways of sachets and filters. More commercial products here for bananas, plums, and strawberries that are used here in the United States. And this is a very nice paper here that shows the efficacy of potassium permanganate beads and how these are related to the relative humidity. Potassium permanganate efficiency is dependent upon the amount impregnated on the beads, the time of exposure, the relative humidity, and the ethylene concentration. So you see here a chart on the right. On the x-axis, you see the percent of relative humidity, and on the y, you see the number of hours needed to remove 90% of ethylene from the room. If you have a low, like 25% relative humidity, you need about 1.5 hours versus 5.5 hours or more when you have 85% relative humidity. So the lower the relative humidity, the more efficient potassium permanganate is. Ethylene oxidizers. This is how potassium permanganate works. It reacts with ethylene and it gives out carbon dioxide and water. All these oxidizers pretty much slow ripening and senescence in the post-harvest life of the product. They can be used domestically or internationally for shipments during ocean, truck, rail, or air. You use them during cold storage to preserve the freshness of the product, and they are available commercially in many sizes and packaging formats like Tyvek or beads themselves. More examples here. Filters. Ethylene adsorbents. These do not oxidize the ethylene in the room, they just adsorb it. And the simplest version of these is activated charcoal. They can act complementary to other technologies like cooling or modified atmosphere packaging, and they potentially have high capacity for ethylene uptake. They can be used throughout the supply chain, and as I mentioned, they only adsorb the ethylene and they don't oxidize it. At the bottom here, right, you see an example of raspberry. We're using a commercial product. It's fresh. This is a purchase day quality stage, and then after 4 days at home, you see how adsorbing ethylene from the container made sure the quality of the raspberries remained at a better stage. Ozone. Here's a chart with ozone, the effect of ozone in ethylene concentration. On the X, you see days of storage from 0 to 120 days, and on the Y, you see the concentration of ethylene ppm. These room contained apples and pears, and you see with gray here the control ethylene concentration raising from 0 in the beginning all the way to 25 ppm, whereas when there was a constant supply of 0.4 ppm of ozone, the ethylene concentration stayed low to less than 3 parts per million. Another example here, we have a sealed container of about 60 square meters at 0 degrees Celsius temperature with 3.8 ppm of ethylene and an ozone generator in the room. You see here how ozone reduces the ethylene, but unless ozone was really high, more than 10 ppm, that's when it only eliminates ethylene in the room. If you have lower amounts of ozone, you get much less of an effect. And there's issues with high amounts of ozone for worker safety and also injury of the fruit, actually, that's the most important. Some examples of photocatalytic and UV systems that exist out there, and this is an ozone system from a company that's not in business anymore, and how these are attached to marine containers. That's a very interesting graph here. It's a bit old, but it's still valid. I will show you here on the X, you see the number of days of storage, and on the Y, you see the ethylene concentration in parts per million. So that's where they stored the product, and then they used, when they just sealed the container, the ethylene amount remained pretty high. And when they vented, it went down to 0 in about 11 days. So let's go to next and see other types of ethylene management. Ethisorb did quite well, but not as well as good ventilation. CA also went down. The amount of ethylene went down to almost 0, but was still worse than good ventilation. Similarly, UV again had an effect, but it took about 17 days to get to 0 compared to 11 for good ventilation. And photocatalytic oxidation took much longer, about 24 days. So you see, the most efficient way of reducing the ethylene concentration in a room is good air ventilation. Another experiment, I think it was done in the United Kingdom, they used household refrigerators, and they had 4 fridges per treatment and 4 fridges for control. They used extra fresh discs, 6, which is quite high of a number. You see them here placed all over the place, and it's potassium permanganate, an ozone generator per fridge, and smart fresh. And you will see here now the ethylene concentrations in these fridges over time. It was 20 days of storage, and you see the ethylene concentration in parts per billion. So for extra fresh, the amount of ethylene remained pretty low, 500 parts per billion throughout. It increased over time. And the control one, you see spikes here, and that's because the door was opening and closing. So when you open the door, the ethylene amount goes down, but when you close it, it builds up again, and so forth. So let's see the results on the products. They stored broccoli, cucumber, green peppers, kiwi fruit, and nectarine. And they found that potassium permanganate or extra fresh improved the quality only of broccoli and cucumber, whereas 1-MCP or smart fresh improved the quality of broccoli. Green pepper, kiwi fruit, it remained unripe, and nectarine. However, out of the 21 products that they tested, very few of them had showed benefits on the shelf life. Ozone did not show any benefits at all. And why did this happen? The ethylene concentrations, as you can see here, never went to 0 or very, very low. They stayed at 0.5 parts per million. Also, it's possible that damage was done earlier during handling or transportation, so the ethylene kept being produced in the fridge. And also the fridge temperatures were lower than typical. As you can see in the chart, there were 29% of them had temperatures lower than 5 degrees, which is what the manufacturer suggests. Another example here, I think this is from Australia. They tested 5 different types of products: butter, lettuce, green beans, orange, strawberry, and broccoli. And they used different temperatures, the 5 degrees for lettuce and broccoli, 0 for green beans and strawberry, and 2.5 degrees for orange. And they had cold rooms with 2 different amounts of ethylene, 100 parts per billion and less than 5 parts per billion, which is tiny. It's very, very hard to detect less than 5 parts per billion. So you see here the shelf life in days. You see an extension of 1 day for butter lettuce, about 6 days for green beans, about 50 days for orange, that's significant, 6 days for strawberry, and about 20 days for broccoli. So you see, as a percentage, a 19 to 147% increase in shelf life when you reduce the amount of ethylene in less than 5 parts per billion. And last, I'm gonna talk about germplasm selection and genetic engineering. Here you see 2 different varieties of rose plants, vanilla and bronze, and they have been exposed to 1 ppm of ethylene for 2 days. The result in the flowers is striking. You can see how this variety is really not resistant at all to ethylene in the room versus vanilla, which does fairly well. I'm not going to go in great detail with this because I know it might be too complicated. Genetic manipulation can modify the ethylene biosynthesis pathway, and the result can be a fruit that ripens very slowly, and it requires additional ethylene treatment to ripen in the end. Also, we can modify the ethylene perception by modifying the ethylene receptors themselves. And here are examples of wild type melons versus RNAi melons treated with ethylene. On the left, the melon has gone bad, whereas on the right, the modified engineered melon is in a good shape. And other examples of fruits, vegetables, and flowers. However, there's a lot of resistance from consumers for edible crops. So how it works, the genetic engineering is you insert a mutated gene in ethylene plants, and then they become insensitive. These beneficial effects also, though, can be inhibited. So you have a problem then when you try to ripen your fruit normally. The use of inducible promoters to engineer plants of ethylene can be inhibited at will, and as I mentioned, there is a big consumer resistance when it comes to edible crops. So people will often not buy your crop when it's been genetically modified. And wrapping up this presentation, I will say again, storage of at the lowest safe temperature and low percent of oxygen, less than 8%, and high CO2, 2% or more, is very important. You should handle very carefully ethylene-sensitive products. You should eliminate sources of ethylene, like avoid mixing ethylene-producing and ethylene-sensitive crops. You want to have a regular removal of rotten or damaged product. You want to keep gas pipes and cylinders away from your storage rooms because these can be a source of ethylene. The use of ethylene scavengers and oxidizers are important because they can oxidize using ethylene using potassium permanganate or ozone, or absorb it from the atmosphere. Last, there is a number of chemical inhibitors like 1-MCP and silver-based inhibitors like silver thiosulfate for ornamentals, which are not good for human consumption. And I think with this, That was my last slide. I'd like to thank Barbara Blanco, Beth Meacham, and Deirdre Holtcroft, who provided some of the slides, as well as Michael Reed, who did some of the work years ago. And I'll be happy to take questions if we have time. Do we have time?